here's something that catches a lot of parents off guard. Your kid can ace calculus and write flawless code, but if they can't explain what they built or design an interface someone actually wants to use, most tech companies won't hire them. That gap between technical skill and workplace readiness, that's exactly what Stemsteam is designed to close. I'm Rajiv Patel, and I've spent 15 years watching hiring managers pass over brilliant engineers who couldn't communicate or collaborate across teams.
You're listening to the STEM Lab podcast. Quick note before we get going. The research, the data, and everything you're about to hear is 100% human verified and written by real authors, but the voice delivering it is AI generated. Just wanted you to know up front. If you've been listening for a while, seriously, thank you. It's always good having you here. And if this is your first episode, welcome aboard. We release new episodes every Monday, Wednesday, and Friday, and they're all built around one goal: helping parents and educators connect corporate hiring trends to real STEM skill development for kids. All right, let's get into what Stemsteam is and why it's becoming a non-negotiable in technical hiring.
So what is STEAM and why does it matter so much in actual hiring decisions? STEAM takes the traditional STEM framework, science, technology, engineering, mathematics, and integrates arts into it. But we're not talking about crafts or decoration here. We're talking about design thinking, visual data representation, CAD modeling, UX prototyping, and technical communication. LinkedIn's 2026 Global Talent Trends report lists cross-functional collaboration and visual communication as top 3 hiring criteria for technical roles. When parents ask about STEAM importance, they're really asking about what employers actually need, not just what sounds good in a curriculum description. Let me be clear about what STEAM actually is. It's an expansion of the STEM acronym to include arts. But the arts component here means design thinking, visual data representation, CAD modeling, UX prototyping, and technical communication. The framework started with advocacy work from Rhode Island School of Design back in 2006. The National Science Foundation formalized it by 2013, and now it shows up in 34% of U.S. school district mission statements, according to Department of Education data. The practical distinction matters a lot. STEM produces students who can write Python functions. STEAM produces students who can write Python functions and design dashboards that non-technical stakeholders actually use. Traditional STEM curricula focus on computational thinking and mathematical modeling. STEAM adds spatial reasoning, wireframing, color theory for data visualization, and technical documentation. All of these are skills that separate junior hires from mid-level contributors in real engineering environments. And here's something important. The arts component doesn't water down technical rigor. It adds technical competencies that most STEM programs completely ignore. Parametric CAD design, schematic documentation, Figma prototyping, even basic video editing for technical demonstrations. A 2024 IEEE study found that engineering graduates with documented design software proficiency received job offers 23% faster than peers with equivalent coding skills but no visual toolset. 23%! That's not a small difference. Now, let's talk about how STEAM learning actually works. STEAM curricula integrate visual and design components into technical projects rather than separating them into art class. The mechanism functions through applied design constraints layered onto engineering problems.
Think about project-based integration for a minute. A traditional STEM robotics project assigns students to build a line-following robot using Arduino and infrared sensors. The STEAM equivalent requires the same technical implementation but adds requirements. Design a 3D printed chassis optimized for component access, create wiring diagrams using standard IEEE symbology, document the build process with annotated photographs, and present findings using data visualization that a non-technical audience can interpret. The technical requirements remain identical. The deliverable scope expands to match workplace expectations. This approach forces students to apply FDM 3D printing knowledge not as a separate activity, but as an integrated design constraint. The printer becomes a manufacturing tool with material limitations, tolerances, and design for assembly considerations, exactly how it functions in product development environments. Stemsteam progression builds parallel competencies through something called skill scaffolding. A Year 1 learner might use Scratch to animate a simple story. That's coding plus visual narrative. Year 2 introduces Tinkercad to design 3D environments for those characters, CAD plus spatial reasoning. Year 3 moves to Python with matplotlib to visualize data from a science experiment, programming plus data design. Year 4 integrates Arduino sensors with custom enclosures and dashboard interfaces, electronics plus industrial design plus UX. Each stage compounds technical skills with design thinking. Here's the reality. Junior engineers don't just solve problems. They document solutions, present to stakeholders, create assembly instructions, and design interfaces. Stemsteam embeds these expectations from initial exposure rather than treating them as afterthoughts. Effective Stemsteam implementation requires software stacks that cross disciplines. For design tools, you need Tinkercad, it's browser-based and free, Fusion 360, which is free for students and runs on Windows or Mac OS, and Inkscape, a free vector editor that works across platforms. These handle 3D modeling, 2D design, and technical illustration. For programming environments, there's Scratch 3.0 with an offline editor available, Python 3.11 or higher with Jupyter Notebooks, the Anaconda distribution works well, and Arduino IDE 2.x, which supports ESP32 and RP2040 platforms for expandability. The decision point between Python and Scratch for teaching AI typically happens around age 10 or 11, when learners transition from block-based to text-based syntax.
Hardware platforms include microcontrollers like Arduino Uno R4 Wi-Fi. It's got 5-volt logic, 32 kilobytes flash, and Wi-Fi connectivity for IoT projects. There's Raspberry Pi 4 Model B, which runs a full Linux environment and supports camera modules and displays. And modular robotics like Lego Spike Prime, which is Python compatible with standardized connectors and reusable across multiple builds. Critical consideration here: avoid proprietary ecosystems that don't prepare students for industry-standard tools. Moving on to why Stemsteam actually matters. The business case for Stemsteam learning rests on employability metrics and skill gap analysis. Technical hiring in 2026 prioritizes hybrid competencies over deep specialization. Let's look at workforce demand data. GitHub's 2025 Octoverse report identified that 68% of technical projects now require collaboration across engineering, design, and product teams. Postings for full-stack developer increasingly list Figma or similar design tools as requirements, not preferences. Mechanical engineering roles now expect CAD proficiency that includes rendering and presentation, not just dimensional accuracy. Stemsteam addresses these requirements at the foundational level, rather than requiring expensive retraining later. Salary data reinforces this. Glassdoor's 2026 analysis shows that software engineers with documented UX and UI skills command 18 to 22% higher compensation than peers with coding-only portfolios. Mechanical engineers with parametric modeling and visualization skills start 15% above baseline. The premium reflects scarcity. Most STEM graduates lack these integrated capabilities. From a practical skill translation standpoint, a student who completes a Stemsteam learning path reaches 16 with a portfolio demonstrating functioning code repositories on GitHub, rendered CAD assemblies with technical drawings, documented electronics projects with professional schematics, and data visualizations that communicate findings clearly. This portfolio directly translates to internship eligibility and scholarship applications. Traditional STEM produces scattered project files and science fair posters that fail to communicate competency in professional contexts. Stemsteam AI Concepts curriculum exemplifies this. Teaching neural networks requires Python competency, that's STEM,
but explaining how the model makes decisions requires visualization of weight distributions and decision boundaries. That's arts. Building an actual application requires interface design so users can interact with the model. That's technology plus arts. Stemsteam frameworks ensure learners address all components, not just the algorithmic core. Now let's talk about types and variations of Stemsteam programs. Implementation models vary based on age, resource availability, and learning objectives. Understanding these variations helps parents select appropriate entry points.
Structured school programs operate at the district level and typically use project-based learning with dedicated makerspaces. They provide access to expensive equipment, laser cutters, CNC mills, industrial 3D printers, but they often suffer from rigid pacing and limited depth per topic. A complete STEM lab setup at home addresses equipment gaps for self-directed learners who want to maintain momentum beyond classroom hours. Home lab implementations for self-directed STEM learning require intentional curriculum planning and staged equipment investment. Parents must ensure projects integrate design components rather than treating them as optional decorations. The advantage? Learners can iterate repeatedly, build complex multi-week projects, and develop genuine depth rather than superficial survey exposure. For age-appropriate progression, here's how it breaks down. Ages 6 to 8 represent the foundation stage. You're looking at physical computing toys like LEGO Education We Do 2.0. Check the show notes for a link to the current price. That combine motorized construction with block-based programming. The arts component emerges through designing functional machines that solve narrative problems, a drawing robot, a mechanical puppet, a sorting device. Focus remains on spatial reasoning and basic sequencing logic. Ages 9 to 11 is the skill-building phase. Transition to understanding sequence, loops, and conditionals through physical play, while introducing CAD design through Tinkercad. Students at this stage can handle dual-screen workflows, code on one monitor, design software on another. Projects should require documentation, assembly instructions, wiring diagrams, usage guides. The STEM skill milestones for 10-year-olds provide concrete capability checkpoints. Ages 12 to 14 is the integration stage. Text-based programming, Python, C++ for Arduino, parametric CAD with Fusion 360, electronics prototyping with breadboards, and data visualization. Students should produce GitHub repositories with README files that include project photos, circuit diagrams, and usage examples. The arts component shifts from aesthetic choices to technical communication and UX thinking. Ages 15 and up represent the pre-professional stage. Industry-standard tool chains, version control workflows, PCB design with KiCad, advanced CAD assemblies with tolerance analysis, and portfolio development. Projects should mirror professional deliverables. Bill of materials, assembly drawings, user documentation, demo videos. This stage prepares students for internships and technical program admissions. Let me address some frequently asked questions. First one. What's the practical difference between STEM and STEAM learning outcomes?
STEM education produces graduates who can solve technical problems using mathematics, code, and scientific method. STEAM graduates possess those same technical capabilities but can also communicate solutions visually, design user interfaces, create technical documentation that non-engineers understand, and prototype physical products using CAD and fabrication tools. The difference surfaces in first-job performance. STEAM-trained individuals require less onboarding time because they already think in terms of end-to-end product development rather than isolated technical functions. Employers report that STEAM candidates demonstrate stronger collaboration skills because they understand design constraints and user perspectives alongside technical implementation. Does adding arts dilute the rigor of STEM education? No, not when implemented correctly. STEAM programs maintain identical technical requirements, same math proficiency, same coding complexity, same scientific method application, while adding design and communication competencies. A STEAM robotics project requires the same sensor integration and control algorithms as a STEM equivalent, but also demands CAD-designed enclosures, professional wiring diagrams, and clear documentation. This increases total workload and complexity, rather than reducing technical depth. The concern about dilution typically emerges from poorly implemented programs that substitute craft activities for genuine design engineering. Rigorous Stemsteam requirements require tool-based design skills using industry-standard software, not decorative arts. At what age should children start Stemsteam learning versus traditional STEM? Stemsteam integration should begin at first exposure to technical concepts, typically ages 5 to 6. Early learners naturally integrate creative and technical thinking before educational systems separate them artificially. A 6-year-old building with blocks simultaneously solves engineering problems, structural stability, and design challenges, aesthetic choices, functional layout. Formal Stemsteam programs simply maintain that integration rather than splitting it later. Waiting until middle school to introduce design thinking requires undoing years of STEM is only math and code conditioning. The transition from block-based programming around ages 10 to 11 provides a natural checkpoint to ensure design tools like Tinkercad enter the workflow alongside increased coding complexity. What hardware investment does home-based Stemsteam learning require?
Minimum viable setup for ages 8 to 12, a laptop running Windows 10 or 11 or Mac OS 12 or higher with 8 GB RAM. That's required for Fusion 360 and simultaneous code compilation. An Arduino Uno R4 starter kit, around $50, a breadboard component kit around $25, and access to a 3D printer through school or library makerspaces. Total cost approximately $80 to $100 excluding the computer. For ages 13 and up, add a Raspberry Pi 4 4GB kit, around $95, a basic multimeter, around $25, and a soldering station if pursuing PCB work, around $60. Avoid cloud-dependent platforms. Students need local development environments that function offline and don't require recurring subscriptions. The complete 3D printer safety checklist for kids becomes relevant if purchasing a home unit, which runs $200 to $400 for entry-level FDM models. How do parents without technical backgrounds support Stemsteam learning? Parents function as project managers and accountability partners rather than technical instructors. Key contributions include maintaining a project schedule, ensuring students document their work properly, asking clarifying questions that force clear explanations, and providing resources, materials, equipment access, online courses. Technical instruction comes from structured curricula, online tutorials, and maker communities. Parents should resist the urge to figure it out together for complex topics. That wastes time and builds incorrect mental models. Instead, identify quality learning resources, Udemy courses for Python, YouTube channels like 3 Blue 1 Brown for math concepts, official Arduino documentation for hardware, and ensure students engage with them systematically. The parental role involves maintaining learning momentum and quality standards, not delivering technical content. Students building best citizen science kits benefit most when parents focus on scientific method rigor and documentation quality, rather than attempting to teach biology or environmental science directly. Let me wrap this up with a summary. What is Stemsteam? Importance of Stemsteam learning comes down to workforce preparation and real-world project execution. The integrated framework produces technically competent individuals who can also design, document, and communicate, the exact skill combination employers prioritize in 2026 hiring. Implementation requires intentional curriculum design that maintains technical rigor while adding design tools and communication requirements at each project stage.
The return on investment calculation remains straightforward. Traditional STEM graduates require 6 to 12 months of workplace exposure to develop design thinking and communication skills. STEAM graduates arrive with those competencies already established, translating to faster advancement and measurably higher compensation. For parents making educational investment decisions, Stemsteam represents the difference between producing a student who can write code versus a young professional who can ship products. The learning path demands more upfront planning, coordinating software tools, maintaining design standards, ensuring projects include documentation components, but the career outcomes justify that additional structure. Technical skills become employable when paired with the ability to communicate them effectively. That integration defines Stemsteam and explains its growing adoption across educational institutions and home learning environments.
That's it for this episode of the STEM Lab podcast. Appreciate you spending this time here. We've got new episodes coming out every Monday, Wednesday, and Friday, so there's always something fresh. If this episode landed for you, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It genuinely helps other parents and educators find the show when they're looking for this kind of practical STEM guidance. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. Thanks again, and I'll catch you next time.